This is the third part of Chapter 16, looking at reactions of alcohols, diols, or thiols. The first one we're going to look at today is called esterification, and we did this in the lab. So you're going to basically use the alcohol and a carboxylic acid to make an ester. This is also referred to as the fissure esterification. So our basic reaction is you have your alcohol. So the H from the alcohol is going to break apart from the alkyl oxy region. Then the acid, you're going to get rid of the OH group, so you're going to basically be dehydrating. And then, of course, the oxygen from the alcohol is going to link up with the carbon of the ester to, of the acid to form the ester. So this portion, so you can see the R prime, and the carbonyl carbon comes from the acid, and this portion comes from the alcohol. So looking at an example, here you have this carboxylic acid, so your benzoic acid, and then your methanol. The methanol is going to lose the hydrogen, the benzoic acid is going to lose the OH group, and you're going to end up forming this ester. Now when you're naming esters, the substituent is going to be the alkyl group without the carbonyl carbon, in other words, the part that came from the alcohol. And the parent's going to be the alkyl group with the carbonyl group, or the part that comes from the acid, but you're going to remove the E and add on the OH ending. So for example, if you're looking back at this one, this will be the alkyl group that came from the alcohol, so that's going to be our substituent, so that'll be a methyl group. And then this would be a benzoate here, because it's a benzyl bromide. A benzyl molecule with the benzene ring and the benzyl carbon. If you're looking at this one, you have one propanol added to ethanoic acid. So our alcohol is going to come first, so it will be a propyl ethanoate for the naming of that ester. You can also use acyl chlorides in this type of a reaction instead of a carboxylic acid. So you'll still start with your alcohol and your acyl chloride. You'll get rid of the chlorine, forming the ester this way. Typically you're going to use a wheat base as a solvent, so this is our pyridine as an example, but there's others as well. So here just shows you another example. This is another example you can see. So here we've got an alcohol, our acyl chloride, get rid of that chlorine, and you're going to, this carbonyl carbon is going to link up to this oxygen off of the alcohol. In addition to acyl chloride, you can use acid anhydrides instead. So here we've got your alcohol, your acid anhydride, remember, is going to have this general formula. You'll break the carbonyl carbon bond here between this oxygen. You'll link up this carbonyl carbon with the RO group over here of the alcohol, and then this remaining region will come and pick up this hydrogen to form a carboxylic acid. So these are some examples. So I'm going to go over some examples on paper so you can kind of see how you're doing. So if it says from what alcohol and acyl chloride or acetic anhydride or acid anhydride would each of these be synthesized? So if this is my substance here, Remember, my RO group comes from my alcohol, and my carbonyl-carbon group comes from my acid. So this would be where I'd break my bond. So my H would go on here, forming our phenol. And then my chlorine would go on the carbonyl-carbon, forming my acetyl chloride. If I did the anhydride instead of this, I would have just two acetic groups on either side, or an acetic anhydride. Look at letter B here. This time my alcohol is going to be from this long chain, so my H will go here off of this oxygen, and then this over here will pick up the chlorine. Or I would have this functional group, O, and then the same functional group again to make my acetic, or my acid anhydride. So my alcohol is my 1-butanol, my acyl chloride is my benzoyl chloride, and then of course this will be my benzyl anhydride. Lastly, this one you see have stereochemistry, so you need to keep it in your structure. So in this particular one, my alcohol would come off of the hydrogen here. So I would keep my stereochemistry in my alcohol because that's where it is. So this would be my E, or my trans 2-methyl cyclohexanol. And then this, of course, would be where I put my chlorine. I've made it as an acid instead of an acetylene chloride. So if that was an acid, that's what it would be. If it was a chlorine, my chlorine would go here where my Cl is. And then my acid anhydride would be this one. So I hope those help you see some examples that are related to that. Now the next thing we want to look at are going to be oxidation of alcohols. This will only involve primary and secondary alcohols, but not tertiary alcohols. And basically what you're going to do are form carbonyl compounds, so they can either be aldehydes, ketones, or carboxylic acids. If you start off with a primary alcohol, you're going to form an aldehyde initially, but if you have a strong oxidizing agent, it's going to go all the way to the carboxylic acid formation. So we'll look at some things where you start off with the alcohol and form the carboxylic acid, and we'll look at some where you start off with the primary alcohol and you form the aldehyde. There has to be a certain reagent in order to stop it at this step and keep it from going on to this step. For my secondary alcohols, it doesn't matter. It's automatically going to become a ketone. Tertiary alcohols do not do an oxidation step like this. So see, our typical oxidizing agents are going to be some kind of a manganese 7 compound, so like our potassium permanganate here, or some kind of a chromium 6 compound like chromic acid or this dichromate acid right here. So just kind of as a review, if we use one of these up here, one of these oxidizing agents that are considered to be strong, and we react a primary alcohol with our either our dichromate or our chromic acid, then you're going to form a carboxylic acid. If you start off with a secondary alcohol and do the same thing, you'll get a ketone. So secondary alcohols always form ketones. Primary alcohols, depending on what your reagent is, whether it's a strong oxidizing agent or not, will depend on whether you form a carboxylic acid or stop at the aldehyde stage. In all of these, you're going to use your dichloromethane as a solvent. Now these two are going to be weaker oxidizing agents. So they are going to allow you, if you have a primary alcohol, to stop the reaction at the aldehyde state. If you use these with a secondary alcohol, you're going to make a ketone just like you would have using a stronger oxidizing agent. So the PDC stands for pyridinium dichromate, and the PCC is pyridinium chlorochromate. So you can just use these abbreviations just to make it easier. But then you're also going to use this as our solvent on the reaction. So if we look at this example, we have this primary alcohol. We're using the pyridinium chlorochromate in the presence of the dichloromethane. And this time you stop at the aldehyde. If we had used the potassium dichromate, sulfuric acid, water, heat combination to make our chromic acid, then we would have gone to a carboxylic acid. So let's look at some examples. This one says predict the principal organic product of each of the following. So this first one, even though we have a chlorine here, that's not going to matter. It's just going to hang on and not do anything. But we're going to be reacting at this end with our potassium dichromate, sulfuric acid, water, and heat. This is a strong oxidizing agent. This is a primary alcohol. So what do you think you should get? Well, you should get a carboxylic acid. So our final product should be 4-chlorobutanoic acid. If we look at the second example, we have this molecule, which is actually a secondary alcohol, reacting with, again, a strong oxidizing agent, our sodium dichromate, and all the other things. So since it's a secondary alcohol, we're going to make a ketone. For our last example, we have another primary alcohol, but this time we're going to be using the PCC, or you could have used the PDC, it doesn't matter, in the presence of the dichloromethane. And since this is a weaker oxidizing agent, then our primary alcohol is going to go to form an aldehyde. Now, an alternative to this is this next step. You might see this in some books. In this particular structure, you're going to use, again, an alcohol. So this is actually a secondary alcohol. So since you start with a secondary alcohol, these are just other reagents that we can use in order to get our final product, which if you start off with a secondary alcohol, you should get a ketone, right? So we're going to use our dimethyl sulfoxide and oxalyl chloride, which is this compound, in the presence of our dichloromethane as our first step. Then we'll use what's called triethylamine. And basically all that's going to do is going to change this to a carbonyl carbon. So we're going to skip some slides here and go to our next reaction, which is our oxidative cleavage of vicinal diols. So basically what you're going to do is you're going to break apart the vicinal diol, and you're going to end up making two products, unless it's a ring structure. So you'll make aldehydes, you can make two ketones, you can make one of each. If it's a ring structure, you're going to just open the ring and put these functional groups, the aldehyde group or the ketone group, on the opposite ends. These are just the byproducts, so this would be iodic acid, this would be water, of course, and we're using periodic acid as our reagent here in this process. So our first example is really basic. So here we have a 2-carbon compound that's a vicinal diol. You're going to break this bond in between the two vicinal carbons, and you're going to get two ketones, since these are carbon groups up here. And our second example, we're going to again break the bond between the two carbons with the OH groups on them, using our periodic acid. And this particular one, since this is terminal or on the end, it would be an aldehyde. On this one, since this is a secondary alcohol group, then you'd form a ketone. So you can either form two of the same kinds of things like you did up here with the ketone. You could have formed one of each, or you can actually form two ketones. Just depends on what's attached to the carbons that have the OH groups on them. If you do have a ring-shaped molecule like this one, then you're going to break, again, the bond between the carbons that have the OH groups on them and just open the ring. And then wherever these are, will create your either aldehyde groups on either end. Should there have been a carbon maybe on one of these or on both of these, you could have formed a ketone groups on either end. So let's look at just a couple of examples. So on this one, we're predicting the products formed by the oxidation of each of the following with periodic acid. So on this one, I just rewrote it this way just to make it easier to see. I'm going to break this apart, and you see that you would get two of these compounds or two formaldehyde compounds, or you can call them methanols. If I look at my second example, I will be breaking the bond here. Both of these are terminal, so I'm going to end up forming two aldehydes. So my first aldehyde is going to be putting my carbonyl group here. So I'm going to get a 3-methylbutanol. My second one is going to be putting my carbonyl group here. So I'd get a 3-phenyl, phenyl being the benzene ring as a functional group, ethanol. This last one, you have a ring shape. You'd break again between the carbons with the OH groups here. Now you can see that this one actually has a carbon group on it, so you're going to end up having a longer carbon chain than a 5-carbon ring chain. Okay, so when you break that apart, you're going to actually get a 6-carbon chain. On the end where this one's attached directly to the ring, you'll get your aldehyde group. On this one, it'll be a ketone group. Now when you're naming something like this, your aldehydes take precedence over your ketones, and then your ketone is given the name oxo to indicate that it's present, or the carboxyl group is present. So I'd start numbering at my aldehyde, because that's always terminal, so that's number 1, 2, 3, 4, 5, so this would be 5-oxohexanal. The last thing we're going to look at in this chapter are thiols. So we're going to just very briefly look at a thiol. When you look at a thiol, thiols are going to have the SH group instead of the OH group like an alcohol, but they do react kind of similarly to the alcohols. When you name these, the final name of the parent does keep the E, whereas in an alcohol it is dropped. So if I'm looking, for example, at this one, this would be, again, this will be my first carbon, so it'll be 1, 2, 3 methyl, and then 1 butane thiol. So let's look at a couple and see if you can draw them. So on this one we have 3 methyl 1 butane thiol. So my butane thiol is going to be a 4-carbon chain, where off of the first carbon I have the thiol group. And then off of the third carbon, so 1, 2, 3, I put my methyl. If I have a trans 2-butene 1-thiol, my SH group is going to be on my first carbon. I'll have a double bond on my second carbon, between my second and third carbon, and then I have to show that it's in a trans conformation. So my trans would show this way, so 1 carbon up, 1 carbon down, or high to low, low to high. And then, of course, this will be off of the first carbon. Now, there's just really 2 main reactions to look at that we're going to look at. There are others, but these are the only 2 we're going to talk about. The first, both of these involve some type of a halide with one or the other of these compounds. So this is going to have the benzene ring, a sulfur, and a metal. You can either use sodium or potassium. If you use this one, you're going to break right here between the sulfur and the metal, and then this whole thing is going to attach to the remaining structure, whatever you're starting with. It's got to be a halide cell. Remove the halide from the compound and replace it with the S and the benzene ring. Or you can use the sodium thiol or the potassium thiol, and the only thing that will substitute on is the thiol group. So let's look at just a couple of examples. So if we want to make this compound, if we want to make 1-hexane thiol, and we want to start with 1-hexanol, this is an alcohol. So we don't have a direct relation or direct method to go from an alcohol to a thiol, but we can go from an alcohol and make an alkyl halide. So that was one of the first reactions we ever did, was taking an alcohol, reacting it with a hydrogen halide, and making it into a alkyl halide. So here, the first reaction, we'll start off with our alcohol. We'll use the hydrogen halide. Since this is primary, you need to use the stronger hydrogen halide. So that's our hydrogen bromide. That's going to do a nucleophilic substitution and put the bromine on the carbon chain. And then if we want to make 1-hexane thiol, then we're going to use either the sodium or the potassium thiol and substitute off the bromine and put on the thiol. If we start with this compound, we can see that this right here, this is our C6H5 group, and this is our sulfur. So we're making this from allyl bromide. So our allyl bromide, just drawn out as this. We'll break our bromine here. We're going to add on this substance. Now this could be a potassium as well. And so you'll break your bond here, you'll break your bond here, and then of course this carbon, the allylic carbon, is going to attach to the sulfur, and that's going to make the desired product.